I'm Sean Kandel, CTO, one of the founders at Trifacta. Today I'm going to present some work we're doing at Trifacta that I've been working on, especially with one of my co-founders, Jeff Hare, who many of you may know from the visualization community. I'd say fortunately, Jeff's second baby is due this week, so he couldn't make it out here. One other thing I wanted to mention, although this is work we're doing at Trifacta, I'm actually going to talk very, very little about the Trifacta product specifically. In fact, all of the visualizations I'm going to show you, we've pulled out into standalone prototypes. If you're curious about how it actually integrates with the product, feel free to grab me after or come by our booth upstairs. So first of all, what is data lineage? I'm guessing if you came to this talk, are most of you familiar with, I guess, data lineage by a show of hands? Okay, great. So this is a definition I pulled off of Wikipedia, kind of broadly speaking, defined as the data lifecycle that includes the data's origins and where it moves over time. So it's kind of a very important concept. I think a lot of people, when they think about data quality or other issues with data, it's often kind of pointed at the source data, but data changes a lot throughout any kind of process working with it. So I think the important thing with data lineage is really keeping in mind that it's important to understand that process that the data goes through. So, why else is data lineage important? Well, it can really be used to answer a ton of different questions about how data is being used within any organization. As an example, which data sets and table columns are driving your key metrics or driving your key reports? How is privacy-sensitive data being used and treated throughout the organization? Again, are the right people accessing it? Are they using it for the right purposes downstream? And then kind of, very broadly speaking, and this is the example that's probably closest to our use case at Trifacta. We're a data transformation company. It's simply understanding what's been done to the data. I think for kind of simple data transformations, it's easy to look at either a script or look at the data and kind of have a sense of what happened. But what we found in practice is that as these workflows get more complex, certain data sets can be joined with dozens of other data sets. Sometimes data is transformed in hundreds or even kind of thousands of ways before you get to your end result. So our goal at Trifacta and with this work is really to help reason about these transformations. Just help a user come in and understand what's happened to my data, help them understand what assumptions they can make, not only about the input, but also the way in which that data was transformed and ultimately the output that might be driving a report, a visualization, or some other analytic process. So on top of this lineage data, what we want to do actually is enable people to visualize this lineage data and interact with that data. And we're not really the first ones to do this. There's been a ton of related work in this field. So I just want to touch on a few different examples to illustrate that when people talk about lineage, it can be at kind of many different levels. Let me start with probably the most common tool that most of our users use, and I'm sure many of you in the room have used, Microsoft Excel. So how many people here have used Microsoft Excel? How many people knew about this track dependence feature that I'm showing up here? Okay, I didn't know about this either until a few weeks ago, but it's actually a really cool feature. You can select kind of any cell in Excel. You can say to track its dependence or track its dependencies, and it'll do a couple things. One, on a given cell, you can perform what we would call backward lineage. You can see all of the other cells that have contributed to that cell's value. So you can imagine you're adding two numbers, and they produce a third number. You can also look at forward lineage. So given a cell, what are all the other cells that depend on that value? So incredibly useful features. What's interesting here with Excel is it's kind of embedded in the data itself. So it's at a fairly low level. So you get a lot of richness about the actual values, but you lose a lot of information about the actual structure of the transformations itself, the script as an entirety, or even kind of how attributes might relate to one another. Kind of at the, I'd say maybe on the other extreme, if you're familiar with ETL tools or mapping tools, this is an example from Tahoe. They'll often provide visual data flows, and the idea here is to take the data flow, And then you're going to turn this into a graph. So each node in the graph is going to be some individual transformation, and then you'll have an edge between nodes or transformations if they depend on each other. So here we see an example where we have kind of one independent stream along the top of transformations, a second one along the bottom. They then become kind of dependent on each other or linked up with this join operation, and then there's kind of further processing done after the join. In this use case, you see the transformation's kind of the first-class citizen instead of the data attributes. So you kind of lose the context of the data, but you get kind of a richer description of what's happening with the transformations. One other thing to note about this visualization is that the transforms are dependent on each other if they kind of operate on the same table. But oftentimes, what we've seen in practice is that you might have many transformations that operate on the same table, but are in some sense completely independent of each other. For instance, you might create one attribute and then create a second attribute. Those transformations might be completely independent of each other, so in some sense, there shouldn't really be a dependency between them. And I'll talk about this a little bit more when we get into column level lineage. Maybe more interesting if you're in the big data space is kind of some of the new tools that have come around with some of the vendors like Cloudera Navigator and Atlas for Hortonworks, where they'll basically capture a ton of lineage, all of the jobs that are submitted to your cluster. They can capture all of the input sources, how that data is transformed, and then kind of written back out into output destinations. I would kind of describe this as dataset level lineage. It's operating at the level of, here are kind of my source files, here's the destination file, or here's my source hive tables. They get joined together to produce another hive table. Typically with these views, you won't get into the details of the actual individual transformations or the attributes being transformed. It would be incredibly useful to get kind of a big picture sense of how data, the actual physical data is flowing through the system. And a similar view here with Atlas. So our focus at Trifacta is, rather than looking at individual values or abstract program data flows, which can be incredibly useful, we also wanted to support a third use case, which is looking at column level data lineage. And the idea here is that we want to understand the relationship between data variables across a series of transformation steps. So we really started thinking about, how can we display these dependencies among data variables as they change over time, as new steps are added to a script, and what we would call kind of logical time. Your transform is getting applied, new rules are being added, how do these attributes and the relationships between attributes evolve? So I want to walk through first kind of the process we went through to build and design and start iterating on the types of visualizations I'll show and some of the interactions. Then I'll show a quick demo and then get into some of the more technical details on how to make the system actually work. So I'm going to start with a very simple example. I'll show you in a second a transformation script. It's only about, I think, 8 or 9 lines. But just to give a flavor of some of the interactions before moving to scripts with many more transformations in them. So for this example, imagine we're doing analysis. So in our case, we actually do have a free tool that you can download and use. So we might have a question on users that register, how long does it take them to sign in? What's that gap between the initial registration and their initial sign-in? Once they've signed in, how long does it take them to actually create a data set? And we might have a hypothesis that users who take long for any of these, between any of these steps, that there's a lot of friction in that initial user experience. And then we might want to test the hypothesis that friction might be correlated with lower activity on our platform in the long term. So I'll show you how we can compute these metrics for some base data and how we can use Lineage to kind of understand all of the computations that are happening. So what does the process look like? First, we're just going to take a data transformation. We're going to analyze all the individual steps of the transformation to detect dependencies between columns across individual transformations. Once we have these kind of pairwise dependencies, we can use all this information to build up a dependency graph, and then we can use techniques from graph visualization to start inspecting and interacting with the lineage. So first, here's an example of what we would call a trifacta recipe, but it's really just a set of transformations. I'll talk a little bit later in the technical details how you can extend this pretty easily to other languages like SQL, MapReduce, and others. But just quickly walking through this step, you can see these first 3 lines: split rows, split, and header. Basically, just taking a raw file, splitting it out into rows and columns, and applying some metadata. We then split this email column on the ampersand, and this will give us a username and a domain. So that's the middle 3 lines there. Then we're going to delete some of the rows that don't have valid phone numbers, or if we have a lot of users at Trifacta or logging in, maybe we want to delete them so they don't affect our analysis. And then we're going to derive the actual metrics I talked about. How long before someone signs in, how long before they're active, and then we'll flag them if we believe there's some delay in the funnel. And then finally, we'll aggregate that data up to produce a report. So this is what it looks like if you were just to kind of look at the textual representation. Remember, at this scale, it's not terrible to kind of go in and reason about it. It does take some time. But again, this is kind of what I would describe almost as a toy example compared to what many transformations look like in the real world. So that's the transformation script. We're going to analyze this to identify dependencies. Basically, we get some intermediate state. It's not that interesting here. The only reason I bring it up is outside of the visualizations I show you, there are a lot of cataloging and other metadata tools that are actually designed to kind of catalog metadata. So this intermediate state can be interesting if it's exposed to those external tools. But for this talk, the main thing is we're going to use this to actually build a dependency graph. And essentially all we're doing is we're going to assemble the output of each of those individual transforms, all of their dependencies, into a larger connected graph. So for the graph, we're going to have nodes and edges. The nodes are going to be unique versions of a table column. So what do I mean by this? Essentially, every time a table column is introduced, a new metric is computed, that will become a node. And then we'll create a new node if that table column may have changed. For instance, the values were updated, or there was a filter applied that may have deleted some values from that column. That'll get a new node. And then we'll have edges anytime that there's a dependency between nodes. And for the purposes of this talk, we've really kind of classified things into 2 types of dependencies. So the first one is what we would call value dependencies or direct dependencies. The idea here is that the values in a column directly derive from another column or a set of columns. So here's some examples from the script, from some other scripts, but say we derive a new column that is the price of a share times the number of shares as order size. We would say order size directly depends on the price, and it directly depends on shares. If we split email out into 2 columns, username and domain, each of those columns now directly depends on email. And then in this last example, if we aggregate up and say take the sum of sales to produce a total sales column, total sales directly depends on sales because those are where the values are coming from, but it doesn't directly depend on location where you're grouping up this data. But that dependency is important, and it obviously affects the output and the report, so we'll also want to track those. So those are what we call condition dependencies. The idea is that the values are kind of changed or modulated by another column, but they're not kind of directly coming from that value. Another way to think of it is if you deleted a value dependency, your script would in some sense just completely break. But if you removed kind of these indirect dependencies, your values would change, but your script or logic would still be valid. So in this aggregation example with total sales, location is now an indirect dependency. These last 2 transforms are interesting, filter and join. Whenever you filter rows out of a data set, you in some sense affect all of the columns. So everything that's in your filter predicate now becomes kind of an indirect dependency of everything downstream. And similarly with the join, your join predicates, in this case if we're joining on item ID across order and items, now is indirectly affecting all of the other columns downstream. And we'll see when we get to the visualization, if you try to look at all of these dependencies at once, oftentimes it can really clutter up the analysis. So we'll need some interactions to deal with them. And then finally, we're going to visualize the graph once we have this dependency. So there's kind of a few ways of visualizing this. The one I'm showing here, and actually I'll just pull this up in Excel. Sorry. Something like, so we've seen actually a ton of our customers, and this is probably the most common way we've seen people interact with this column level lineage. Let me blow this up. Where you'll keep basically a spreadsheet, or you might actually store this in a purpose-built cataloging tool where you have kind of for all your tables, all of your columns, maybe, is it a derived column? Is it a raw column that came from the original data set? Maybe kind of a description of what that column should be or what that metric should be, and then maybe the formula. So this is actually a decent way of storing the data. Again, many people do it this way, but it becomes really hard to kind of track all of the dependencies. For instance, here we have a column mean job run count, which is produced using an aggregate, which depends on a column called delay and funnel, which itself was derived. So you get in this process of then kind of tracking back manually through the spreadsheet, looking for all of these dependencies. But this is certainly a viable option. Kind of the next thing most people would think to try when looking at a graph is some type of directed graph. So this is a very common way of visualizing nodes and edges. And in this case, as I mentioned before, we'll have a node for each unique version of a table column, and then we'll have a solid line indicating kind of value dependencies or direct dependencies, and dotted lines indicating conditional dependencies. If you try to do this on scripts of any kind of real size, you run into a number of issues. The first one is that you're kind of completely missing the context of the transforms. The whole layout now is determined just by the dependencies between the nodes. So if you do have a script in mind, or you do have some context based on the transformations, you've lost that. And this leads to a few things, such as kind of the second problem here, which is you get really inconsistent node placement. So if you're trying to visually scan through this graph and kind of track nodes and how they evolve, it becomes difficult because the placement, again, is determined by the layout and loses kind of the structure of the transformation. And then finally, as I mentioned before, when you have a lot of conditional edges, which happens with things like filters and joins, you can lead to a lot of visual clutter. So to tackle this, we actually turned to some inspiration from timelines and genealogy visualization. So there's been a lot of work here, dating back actually kind of hundreds of years. So this is some work, or an excerpt of work done by Priestley in the mid-1700s, kind of the first, or one of the first examples people think of a timeline. So the idea here is that you can see when kind of important historical figures, when they were born and when they died, and you can quickly start getting a bunch of information out of here, such as, when did people overlap in time, who kind of operated before someone else in time, and so on. And this is just an excerpt, but kind of the original of this, I think, displayed about 2,000 different individuals in the chart. So you can store a lot of rich information in these timeline views. Of course, these have kind of progressed over the years. So this is now famous excerpt from XKCD comic. So Monroe, about 5 or 6 years ago, came up with this Lifeline depiction where you're displaying individual characters in certain stories. So on the top, Lord of the Rings, and on the bottom of Star Wars. And the lifelines will kind of come together and diverge as individuals come close together in the storyline and drift apart. So again, you can get really kind of rich information about the relationships between individuals in this case, and how those relationships change over time. Actually, I think I need to plug in, maybe. Sorry about that. Jump around here. Over there. Thanks. Thank you. On a similar kind of strain of work, TimeNet's genealogies, done out of Stanford a few years ago, where they were looking again at kind of family trees and genealogies, so looking at the relationships between individuals. Here, lifelines come together as people get married, and then they'll diverge as people get divorced. And then you can see these drop lines indicating children. And from this these just three kind of simple things, you can see a lot of relationships really quickly, like marriage, divorce, remarriage, children that are born out of wedlock, all are kind of readily available from charts like this. And what's interesting, if you remember going back to the directed graph we started with, in this paper they actually evaluated these two charts side by side, or chart types, where they would give people a bunch of tasks to track dependencies. And they kind of looked at two different types of dependencies: structural dependencies. So something like an individual is the child of someone else, and they would ask them to identify or verify that in the chart. And then temporal dependencies, so looking at how structure or other relationships change over time. And what they found was that with the visualization on the right, you could kind of just as quickly and as accurately identify structural dependencies, but temporal dependencies became significantly easier to read off these charts. So based on that, we've decided at Trifacta to take a different approach instead of going with the typical directed graph. And instead of applying the Lifeline concept to individuals, apply it to data fields. So this is kind of an initial static view where we're going to lay out the lineage data in a tabular Lifeline layout, where each individual column in the table will correspond to a transformation of being applied to your data. And then the rows will correspond to columns that will disappear as they're dropped and come into existence as they're created. And I'll go into a demo quickly, but just to give you a sense of some of the interactions, the idea is that we want this chart to be interactive. As you interact with columns, you can trace back and see its backward dependencies. In this case, the yellow lines are indicating backward dependencies for time before sign-in. And you see you see that this is a derived transformation. We can see immediately that there's two direct dependencies feeding into it: registration time and sign-in time, which makes sense. We're computing the time it took between registration and sign-in. And then those two columns themselves have more downstream dependencies that might be interesting. Similarly, going forward, we see that there's a number of columns that depend on time before sign-in. Kind of the first one is this delay in funnel, which is just going to be a flag indicating whether it took a long time for someone to sign in. And then one other note, the value dependencies are solid lines, and the condition dependencies are indicated here with dotted lines. So with that, I'm going to jump into a demo. I'm going to start off with, again, a simple kind of small example, the same script I showed earlier. So we can see here, again, there's about 10 transformations in the columnar layout. We can see the first few where we're kind of just splitting out the data and metadata, and you can kind of scan the transforms as you go across this way, from left to right. And then the individual attributes are stored in these columns here. So let's just start interacting with some of the attributes. We'll take a simple one here, like username. When we select username, we immediately, again, kind of query the lineage data to find just its dependencies. So we can see here that username depends on one column, email one. Why does it depend on that? Well, you can look at the actual transformation itself if you're curious, and you can see that we simply rename that column to username. So this column disappears and now becomes username. This column here is also, email one is now dependent on another column before email, which again makes sense. We saw before that we were just splitting that email into two separate attributes, the username and the domain. Similarly, if we look kind of going forward at the forward lineage, we see only one column depends on username, which is itself later on. And when it changes or creates a new version because the table went through a filter or delete, where we deleted some rows. But actually, kind of interestingly, you can immediately see that that column is actually not even used downstream by our final result, which is an aggregated data set. So already you can kind of spot an opportunity maybe to optimize this script and get rid of data potentially earlier on. So let's look at another column, domain. We see here, similar to username, it depends on one column before it, email 2, which itself was split out of email. But unlike username, there's actually a ton of columns downstream that depend on this value. So why is this? This goes back to what I mentioned before with indirect dependencies. We noticed before when we were deleting that data, we were deleting any rows where the domain was from trifacta.com. So in some sense now, domain is actually affecting all of our values downstream. As I mentioned earlier, when you introduce these indirect dependencies, you can see that there's a lot of clutter, a lot of additional richness that you might not necessarily care about. So I'll show you in a little bit how we can start filtering down this chart to just zone in on the information that's important for your analysis. So let's look at a couple other columns. I showed this before, time before sign-in is derived from these two attributes. If we wanted to look at time before active, something similar, again, derived from two different attributes, and then delay and funnel is coming from both of those attributes as well. So we can select individual columns, or if we like, we can actually select entire transforms. So now we can see, well, what are all the dependencies for the final output of our results? So again, we're producing an aggregated report, which is going to compute a couple of metrics where we divide up our users based on whether or not they experience a delay sometime during the funnel. And we can see here, again, kind of a rich set of dependencies going back that we could track down. Again, this can become kind of tedious when you have a lot of rows and columns. So we might want to actually support other operations such as filtering down this lineage view to just kind of hone in to just the dependencies we care about so that we can track those more easily. Once we've kind of eliminated a lot of the edges that aren't directly affecting our data, we can go even further and collapse down this chart now to remove whole transforms that really have no impact at all on our final results here. And then, of course, we can reset to get back to our original graph to then explore other attributes or relationships. Going ahead a bit, this is just a single data set. In many cases, you might have multiple data set relationships where you're joining in other data sets. So in this case here, we can see we've done a few transformations. We've then loaded in an external data set, joined that in, and then again performed some more operations. So what we'd expect with the join, again, is some conditional dependencies. For instance, if we select a column here, mean duration, we can see it has a value dependency back to its direct descendant here, or direct ancestor, but also now two conditional dependencies on account ID, where we're joining up accounts across these two tables. And again, if we like, we can collapse this down to just focus in on the attributes that we care about. Similarly, the other common way of joining or combining data sets is through a union operation. If we look at kind of the downstream output, you can see each of these columns depends on multiple external tables that have all been unioned in together to produce a merged data set. So those three examples, again, I'd kind of describe as very small examples, very small scripts. So we wanted to see how we can apply some techniques to interact with Lineage over dozens and hundreds of transformations. So here is another visualization here, except this time we've loaded it up with a lot more transformations. So you can immediately see it becomes much more difficult to reason about what's going on in this graph. So we'll need some more interactions to deal with that. So the first thing you'll kind of notice is as you scroll left to right, we'll kind of freeze the existing headers on the left. So at least you always have a sense of which columns are available in the view. But additionally, we've provided what we call an overview mechanism. So one interesting thing is, and we notice this in a lot of our customer scripts, is that when these scripts get long, oftentimes it's because users are doing a lot of repeated interactions. So what happens is you get a lot of subgraphs in your graph that have very similar structure. So we provided what we call the overview feature, which will try to identify these kind of repeated steps or substructures and then reduce down this script into a much smaller graph. So we can see here, we've now reduced this down into about a dozen or so steps by collapsing certain steps. Do that again. All right, so this helps with the analysis, but even then, there's a lot of complexity. So we can use some of the same techniques I mentioned before. So let's actually go and zoom in here on the last column in our data set. We might be curious just about this last attribute. Again, just doing a simple collapse, we can get down to a much more manageable script, and we find that this is often the case, where you can narrow it down to just a handful of transformations and dependencies to track. In other cases, what you want to actually do is compare not data across every individual step, but just across a certain set of transformations. So in this case, let's actually take a transformation early on where we first assign metadata, and then we can compare this to our final operation here by selecting both columns and saying compare steps. This now will reduce the graph just to the nodes that you selected, and you can very quickly see from your output data set what are the input columns that are contributing or affecting that column. So those are just some of the interactions you can apply to answer some of these lineage queries and understand relationships. Now I want to jump back into some of the kind of more technical details on how to actually build these visualizations. And we'll talk about a few different aspects. The first thing is dependency parsing, where we're just going to analyze the program to determine the relationships and build up this dependency graph. It's actually fairly straightforward. The only thing I think really of note to say here is that most languages, whether it's Trifacta or SQL or Pig or Spark, underlying them, there's only really usually a handful of kind of core operations or ways of fundamentally changing the data. So if you can implement dependency parsing for what we would call kind of primitive transformations or operations, you can then use this to build up dependency chains for other types of transformations. For instance, if you're familiar with lookups, that can be will have the same dependencies as if you kind of translated it to some type of join. For pivoting data, that can be translated into a map and aggregate, and so on. So you can get kind of the richness of transformations actually by just implementing a kind of a small handful. And that allows you to quickly kind of port these same types of visualizations onto other types of languages. For the lineage queries, it's simply a graph traversal. So we're just going to follow dependency links, either their targets or their sources, and we can just kind of recursively or iterate down the chain. And then one interesting thing here is that all of the filtering and collapsing and all the ways that you can interacting with the chart can actually be driven by just a single operation, which is to apply a predicate to the nodes you want to keep. So those are the column versions or the attribute versions that you want to keep. And then you just perform a graph traversal to rewire those remaining nodes. So to make this a little bit more clear, if you have an input graph and you want to remove some nodes, we can apply a predicate. So now we see two of the nodes are going to disappear. We then need to analyze the links or reroute those links so that all of the dependencies still stay intact, even though some of the intermediate nodes are gone. And then we can produce an output graph. So it's a very simple procedure, but it can actually drive a ton of different interactions and ways of viewing those dependencies. The next thing is the Lifeline layout. There's exposition, so where the actual nodes are placed on the x-axis isn't that interesting. It's in some sense pretty much fixed based on our layout because it's in the order the transformations are applied. There are some details with collapsing, so you want your kind of scale to be aware of this distortion. But probably a little bit more interesting is determining where those the Y positions are. So as new attributes come in or ones are deleted, where do those columns get placed? So you could imagine doing actually some type of global layout where you try to minimize the distance between columns that have dependencies on each other. If you do that, you actually end up with fairly unstable visualization where column attributes can shift pretty wildly throughout the transformation script as dependencies are introduced and changed. So instead, what we decided to go with is a more stable layout where essentially once a column gets a Y position, it essentially stays there for the rest of the visualization. And instead, dependencies are placed as close as possible, or value dependencies are placed as close as possible to its parents. Finally, a couple of notes on the transitions you saw when we would kind of filter down the graph. There's a few tricks you need to do to make this seem stable. Actually, when you're doing this over large graphs like the one I just showed, there can be thousands of nodes on screen and tens of thousands of edges, and you want kind of stability as that chart is animating. So one thing you may notice if you all use D3 is that, at least in version 3, when you animate a number of elements, the transitions aren't synchronized. Luckily, this was updated in version 4, but it's crucial that as you're animating, all those transitions start at the same time, or it'll create a ton of strange effects that can be jarring to users. Finally, the stability of the visualization. Again, we're actually transitioning and filtering a ton of elements on screen at once. And if you imagine doing this naively, you would animate both kind of the visualization or the kind of SVG components as well as the browser simultaneously, which will lead to a ton of different artifacts with scrolling and again, perception of where these elements are. So a nice trick here actually is to instead only animate the SVG properties and completely ignore the browser properties. But to make, again, this look stable, the trick is to basically automatically adjust the offset so that the origin of the canvas now lies at scroll position 0. You then do the animation of the SVG elements, and then you can then readjust that offset so you're back at the proper browser scroll position. Again, these seem like small details, but without these effects, you get very jarring effects, or very jarring interactions over this graph as you filter it and interact with it. Finally, another note, which is pointing more to some ongoing work that we're doing, which is really looking at how we can leverage profiling information within the lineage view itself. I showed a number of filters based on either kind of transformation types or the types of dependencies or columns you want to look at. But many transformation tools, including Trifacta, nowadays actually will profile all of your data, producing things like the number of missing values, values that are the incorrect type of data, will compute the distribution, and so on. So kind of an obvious next step is to filter down this lineage view, not only on attributes of the script, but on attributes of the data itself. So some examples of that, find transformations or dependencies that are reducing the number of rows in my output. Or you could find transformations that introduce erroneous date time fields, or all of a sudden the number of missing values increases, or even kind of more nuanced stuff like things that are dramatically changing the distribution of values in a column. So with that, just conclude with a couple other next steps. As I mentioned earlier, we showed this on top of Trifacta scripts or transformations, but you can, of course, apply this to kind of any language for data transformation, assuming you can build that dependency graph. And you can also apply it to database query plans to help you understand what's happening for tasks like optimizations. As I mentioned already, kind of some future extensions to this work, incorporating profile data. Of course, once you've tracked these dependencies, you can do optimizations to kind of rewrite the script, both in terms of optimizing performance, but also optimizing how well it can be understood when reading it. And then finally, looking at supporting these types of lineage queries, not just over a single transformation, as I showed, or script, but a corpus of this across an organization. And then finally, again, if you're more interested in how this actually integrates into Trifacta and the work we're doing, all this is coming in our version 4. And if you have any questions, happy to take them now or at our booth, number 539.